Hi there, Manu here with the next tutorial of the particle series. This time this is part 2 of particles 5. Last time I told you that I will come up with a second part because we did not finish the setup, and we will do so today. Let's extend on what we did last time and let's make this setup a little bit more intricate by adding little branches to our stems. So remember what we did last time? We created these little growing stems with leaves attached to the ends. And today we want to add branches to these with more leaves. So let's dive into the PopNet and let's see what we can do here. Last time we created particles and then we replicated these particles and created a new particle stream that is then turned into primitives by the add sub one level up. And today we want to create a new pop replicate to create even more particles. But we don't want to replicate the particles all the time, like with the B stream. Instead, we want to burst new particles every 12 frames, say. That will create little branches that go outwards here every 12 frames. How can we do this? Well, first we have to set up some attributes. So, before the pop force and after the initialize, let's introduce a new pop wrangle. Put it here, and let's call it setSplit. And we will use this wrangle to set the attributes necessary for the next pop replicate. Open the expression editor, and inside here we want to create a condition that only executes every 12 frames. That can be done with a modulo statement, so write if add frame, which is the current frame, and then this %sign, and this stands for modulo, and modulo gives the remainder of a division. And let's say 12. And then compare this to 0. So this means whenever the remainder of the division of frame by 12 is 0, the code will get executed. And that is true every 12 frames. So brackets. And what do we want to do whenever this is true? We want to create an attribute to control the pop replicate. So let's invent a new attribute. Let's call it split and set it to 1 in this case. So whenever the frame is divisible by 12, split will be 1. But we have to care about all the other frames too, so let's create an else statement. So whenever this is not true, add split will be 0, like so. And because this is just a one-line statement, the brackets are not necessary. So press apply and accept. And now let's use these attributes with a new pop replicate. So create a pop replicate again. And now let's talk about these two inputs. You have an input on the left and the input on the right, and if you hover over them, the tooltip tells you that this here is the points to replicate and this is the reference stream. What does that mean? Well, in reality, both inputs serve pretty much the same purpose. It is all about how the streams are handled. If you pipe the particles to replicate into the first input, everything that goes out here will be a mixture of the stream coming in and the stream of the particles that are replicated. So if I attach a node afterwards, it will act on the incoming particles and on the replicated particles. But what if I want to control the replicated particles only? That is when input 2 comes into play, this reference port. So if I connect this here to this reference stream, you see I get dotted line, and that means that now everything that comes out here is just the replicated particles, and if I attach nodes to this output, they will only act on the replicated particles, not on the incoming particles. To have all the particles in the output of the pop solver, or solved by the pop solver, I have to then merge these particles with the main stream down here. So this is basically a control thing. So it is there to be able to do a different network setup to put nodes here that only affect these particles. So that means we now put this input stream here in this second port, and then we connect this to the wire pops into here, merge, and you see we get more particles. Now let's put the correct settings into this node. First go to the birth tab, and again we don't want to have any constant birth. Instead, we want to set it to 1, 1 here on the impulse, activation and count to create one particle per incoming particle. And then we want to use the emit from attribute and set this to split, because we just created the split attribute. So let's see what this gives. Let's rewind and play. And you see, every 12 frames a new particle is created. And to see how this stream thing works, if we now create a pop color and rewind, you see that only these newly created particles are turned purple. Everything else turns white, and that is because as soon as you put a color on any particle, the attribute will be created and the default is white. So without the attribute created at all, the particles are black, and with the attribute created, they are white. To avoid this, we can just create another pop color and put it here after the A stream, and let's say make it red, like so. And now we can see the different particles. So the trails are red too, because they are inheriting this color attribute, and the A particles are red, and the newly created particles are purple. Next, go to shape and set shape to point, because we don't want to have the particles scattered on a sphere. And now you see the particles are created exactly where the parent particles are, and they are inheriting the velocity, and they are flying with the velocity that they inherited on birth time. That is, in this case, exactly what we want. Rewind and let's give this pop replicate a more descriptive name. And as we already created stream A and stream B, let's call this stream C. Now, to be able to initialize the new particles with values, we do the same thing that we did last time, and we want to use this JustBorn group. And this feature is available on our pop replicate too. Here you find the JustBorn group, and let's call it CBorn in this case, like so. And that means that we now can create a new wrangle, pop wrangle, and append it beneath. Set the group flag here of this wrangle to CBorn. And that means that this wrangle will only be executed in the very first time step where these particles exist. So we can use it to initialize these particles. Rename the node to initialize particles. And now we can write code here. So open the expression editor. At the moment, the particles are born, and then they are just flying with the same velocity that they inherit on birth time. Turn off these numbers, but that is not exactly what we want. Let's make them fly outwards, so orthogonal to the stems. And we have to think about the angle that these particles should fly off. If you quickly go to Wikipedia and look for the golden angle, you see this image here that a lot of plants use the golden angle, that is roughly 137 degrees, to rotate the leaves around the stem. So the angle between two successive leaves is roughly 137 degrees with many plants. So why not using this golden angle called phi to create directions for our branches? So let's do that. First, let's define phi. So a new float called phi, and this will be 137.5 degrees. But as we want to use matrices to determine directions, we need this in radians, so wrap it in a radians function, radians, the radians of 137 degrees. And what I want to do now is I want to create a vector triple from the velocity to create a little matrix, and then I can rotate this matrix around the velocity to create different vectors for these particles to use as their velocity. So let's create a vector called x, and this vector will be the normalized cross product. Normalized just creates length 1 of a vector, and then cross for cross product between the velocity v at v and the z direction. So this is 0, 0, 1, like so. And then we have to close two brackets. So what this does is it takes the velocity of the newly created particle, and then it takes the global z direction, which is pointing in this direction here, and then it creates the vector that is orthogonal to both of them. So that is pointing in roughly this x direction here. Then we need a second vector, the y vector, so vector y, and that will just be our velocity, but normalized. So normalize again. Normalize v at v, like so. And now the third vector to form a matrix is vector z, and that is just the normalized version of a cross product between the x and the y that we just created, like so. Now we have three vectors that are orthogonal to each other. And the y vector points along the velocity. And that means, because the velocity is inherited, it points along the stem. Now let's create a matrix from these three vectors. So matrix 3, it's just a rotation matrix. Call it x-form, and set it to x, y, and z. Nice. Why this hassle? Because now we can use the rotate function. The rotate function takes a matrix, in our case the matrix x-form that we created, and then it can use the angle phi, and then it can use the axis to rotate about, and in our case it's just y, like so. So now it rotates our matrix by phi. Great. And what we can do now is we can just extract the z-axis from this matrix and use it as a direction vector. So let's create a new vector attribute, v at, and let's call it my direction. My direction, and that will be set. And now comes the shortcut syntax for reading the component of a matrix, and that will be the x component of our vector will be the x component of the z vector of our matrix. So x-form is our matrix, and then dot z, the third vector, and the x component. And then x-form z, y, and x-form z, z. So this will extract this third vector from the matrix. And as the matrix is rotated, this will be the rotated vector, my direction. And now we can just temporarily set v at v should be v at my direction, like so. Let's see if we have any errors. Press apply. Seems to work. Let's rewind and let's see what we have now. And now you see that these particles are created and then they are traveling away from the stems in a 90-degree angle. That is looking more like branches. But we are not done yet, because at the moment they are all rotated by phi. But what we want to do is to rotate them incrementally. So the first particle should be rotated by phi, the second one should be rotated by 2 phi, and then 3 phi, and so on and so forth. So a cheap way to achieve this is to multiply this phi here by at id. Because the particles get an ID of 0, 1, 2, 3, and so forth. Let's see what this gives. And now you see that each particle is rotated by another phi around this stem. Before we continue working on these particles, let's first make sure that they get trails, like the red ones. And that is not hard to do, it's just a little rewiring. At the moment we are creating the trails here with this B pop replicate, and that is before the merge. So of course these particles do not get trails. So let's try to put down another merge. And let's put this merge before the pop replicate here. And then let's cut this connection and let's merge this stuff into this first merge. Let me clean up a little bit. like so. And let's see if this is working. And it is. Now everything is trailing. And it's easier to see how the newly created particles fly now that we have trails. And you see, this is looking funny, but it is not exactly nice, because what we intend to do is to have them first go in the direction of the stem and then bend over to fly in this direction. And that is the next thing that we have to do. To make this work, we have to first get rid of this v at v is v my direction here, because we do not want to do this. Instead, we want to create a new attribute, and let's call this v at parent direction at parent, or parent v, say, parent velocity, and set this to v at v. Man, v at v, like so. Why parent velocity? Well, remember, this here is only executed directly after the new particles are born. And when they are born, they inherit the velocity from the parents. So when this code executes, this velocity is the parent velocity. And we set this to parent velocity, just because we want to use it now in a new operator. And the velocity gets integrated all the time and changes. And we want to just save this value into a new attribute to have it unchanged in the next operator. Now I want to do something different. I want to use a VOP this time, a pop VOP. I want to work with nodes instead of code now. So I append this pop VOP here. And we want to code something that makes these particles fly a little bit more beautifully. Call this pop VOP set direction. And dive inside. The first thing we want to do here inside is to bind the two vectors that we just created. That is my direction, that is the direction you see here, and then the parent v. So lay down a bind, switch it to vector and call it parent v, and then just duplicate it and call the second one my direction. Now we have these two vectors. We can quickly test if this works if we just get parent v and connect it to v here. Now we are setting the velocity to parent v, and you see the stuff is flying upwards with the inherited velocity. We change this, and use my direction instead. We are back where we were before, and they're flying outwards. So why don't we just mix between these two vectors? And we can do so by using the age as a bias. So first lay down a mix and connect the two vectors. First parent v to the first input and my direction to the second input. And then we have to set the bias. And we will do this based on the age, but not directly. We have to fit the age first. So lay down a fit range and connect the age to the value. So the age comes in. And what we want is that when the particles start out, they should use this parent v direction, and the older they get, the more they should fly in this my direction. Let's make this happen over 2 seconds. So the source min will be 0, the source max will be 2, so whenever the age is 2, the max will be reached, and the output range will be kept at 0 to 1, and then we can connect this to the bias. And if we now connect the output of this mix to the V port, look what happens. Now they are starting out in the inherited velocity direction, and then they are bending over to fly in our outward direction. And that really looks very natural. That is nice. But the same problem occurs as last time. They never slow down. They are fast all the time, and we want to make them slow down. And we can do this by just multiplying this output vector, because now the output vector has a certain length. And what if we just first normalize it to make it always length 1? Now we can use a multiply to change the length of this vector. We can multiply it by 0, it will be 0. Or if we multiply it by 0.5, it will be half as long, and that means the particles will travel half as fast. And we can control this by second fit. So lay down another fit range and connect the h to the value, like so. And now say 0 to 2.1 will be 1 to 0. That means when the particles are very young, they are fast, and then they get slower and slower and slower and slower. And I just put this 2.1 here because I don't want to reach 0 too early. And now connect this to this input here and connect all of that to V. And let's see what we have now. Now they are flying outwards. And they are slowing down, and then they are halting. This looks good. But we have another problem. You see that the red stems stop growing and still new branch particles are created. Let's quickly fix this before we continue. And that can be fixed here on the master stop node. We have this condition here where it says execute this code whenever age is bigger than stop on the parent particles. And we want to add a line here. And this line reads at split is 0. And that means no matter what the set split node calculates, whenever age is bigger than stop, set split to 0. Let's see if this fixes our problem. Branches are created, and then no more branches are created. Cool, now we have branching structures, looking a lot more interesting than before. Now let's deal with another problem that we know from last time. If I turn on point numbers and press play, make it grow, you see these numbers keep on counting up. That means these particles here are replicated all over again and again. And we don't want that. Fortunately, we can stop this exactly the same way we stopped it last time, with a stop value and then this stop node here. Last time we created a value on the initialize called stop, and we will do the same thing this time. So go to the initialize particles on the C stream, and at the very top, let's introduce a new variable called add stop, but this time called stop C. And that is just because stop will get inherited, and we need a new value just for these particles. So stop C, and in this case, all particles should have 2 seconds as a stop value. And now we can just duplicate the stop from the first stream and put it here down below the C stream. And let's change this code. Some of it is valid and some is not. So what is valid? If age is larger than stop, what should happen then? Well, then we just want to stop trailing. So delete all of this and instead put trail is 0 here. And don't forget the add. So many typos is 0. So add trail is 0. That is the solution we had last time in the beginning, and this intricate solution can be deleted because this time these particles are stopping after 2 seconds. The slowing down is done analytically, and so we don't have to compare the velocity vector anymore. But we can keep this orient because we want to attach leaves later on to these particles, and for this orient is helpful. So press apply and accept, rewind and play. Oh, and turn on point numbers and see if it's doing what it's intended to do. And yes, if they stop growing, no more particles are created. So we fixed that. Great. Let's go one level up and see what happens to our setup here with the add sub. Let's press play. Oh dear, this is a mess. You can quickly go to unlit to see what's happening here, and the new particles mess everything up. And if you think about it, that's no wonder, because we are using the connect attribute to tell this add-sub how to connect these particles, and the new particles don't have a connect value. So how can we apply a connect value to the new particle such that this works again? Each individual strand here should have a unique connect value. And at the moment we are putting connect values on these master stems and no connect attributes on these small ones. So we have to find a logic that gives unique values to all of them to make the add work again. So go to the popnet again, and then to the initialize of the main particles. And here we say iConnect is ID. Let's create a new attribute and set it to connect for the C particles to inherit, because eventually they should create an own connect value. So it is not a good idea to inherit connect directly. Instead, it is a better idea to create a new attribute. I name it child count and just set it to add connect, like so. This allows me to do the following. I can go to this set split, and now in this set split I can say I add child count ++. That means whenever a new child particle is created, the child count will be incremented by 1. And that is not possible with the connect attribute, because otherwise I will mess up the connect attribute on the master particles. But with its second attribute, this is fine. And then this child count gets passed on to the C particles. And there, in the initialize particle C, we can go to the very, very top and just say I add connect is I add child count. So we read this inherited attribute and set it back to connect, because connect is what the add-sub needs. But it is still not working yet. And that is because if we just increment this connect attribute, we still mess up things. Because at the moment we are creating values for the master particles of 0, 1, 2, 3. And for the master particle 0, we increment this value by 1 for the first child, and then we have 2 times the value 2. The second master particle would get 2, and the first child of the first master particle would get 2. So we have to make space for these new incremental values. And we can easily do that. We can just multiply this ID here by, say, 100. So that means the master particles don't get the connect values of 0, 1, 2, 3, and so on, but instead they get 0, 100, 200, 300. So for every master particles, we have 100 values free for the children. And as we never reach 100 branches per master particle, that is totally okay. So that means now the connect value is 0 and then 100. And here we increment this child count. So for the children it will be 0, 1, 2 for the first master particle, or 100, 101, 102 for the second master particle. Then we inherit it here and write it to iConnect. And after this procedure, all the particles should have unique values. Let's see if this fixes our problem. And let's press play. And yes, it does. Now that all the particles have unique values, you see that we get correct strands, because the add sub now knows what exactly to connect. If we turn on the shading again, you see now we have these nice branching structures. Okay, so we are more or less done. Some finishing touches. Let's make the leaves scale. At the moment the leaves start out big and they stay big. It would be nice if they start out small and then grow too. And we can do this by just setting p-scale. So introduce a new point wrangle. That was wrong. A new point wrangle. And put it here and call it set p-scale. Set p-scale. And let's tie the p-scale to the age. So add p-scale is fit the age at age of the particle, comma 0, comma at stop, and then say start with 0 and end with 0.4, like so. Let's see what this gives. This works. They are starting out small and then they are growing bigger. Maybe let's decrease the width of these things to 0.5. That looks better. And now let's put leaves on all of these branches. And that can be done by going to this blast here and including stream C here. That is our stream, and we get immediately leaves for all the other particles too. And because of the orient, they are oriented correctly, but what happens here? They lose the orient and all look in the same direction. And that is probably an error. Let's go inside into the stop. And I guess that here, as we copied this stop node over, we forgot that we have to compare here with stop C instead of stop. That is a problem. They stop too late. And now it is working. They are growing with leaves and the leaves are scaling up. Isn't that beautiful? And now finally we can go to our scatter and set this to 200, say, and go to the PopNet simulation, reset the simulation and rewind. Reset the simulation and let's see what this gives. Cool. A lot of plants growing in a noise field with a lot of branches and more leaves. A very intricate natural simulation. So that concludes how you can use particles to generate procedural geometry. And you can really go wild with these systems because that is basically an ecosystem. So you could introduce nutrition and lighting to make the growth dependent on different factors and make it all more natural. And then instead of using these very abstracted leaves, you can go for real leaves. And that really makes for a very nice ecosystem simulations. So particles are not only usable as little dots, but to generate ecosystems too. I hope you enjoyed this tutorial. I enjoyed to create it a lot. And follow me with part 6 of particles that will be released soon. Thanks for listening.